Imagine a universe where most of what exists is completely invisible to us. No, this isn't science fiction. It's the reality of dark matter, one of the greatest unsolved mysteries in modern science. Today, we're diving deep into what dark matter is, why it's so elusive, and how it shapes everything we see in the cosmos. Buckle up, this is going to be a cosmic journey. First things first, what is dark matter? It's an invisible substance that makes up about 27% of the universe's mass and energy. We know it's there because of its gravitational pull on visible objects, but we've never directly detected it. It's like the unseen scaffolding holding galaxies together. Unlike ordinary matter, stuff like stars, planets, and you and me, dark matter doesn't interact with light. It doesn't emit, absorb, or reflect electromagnetic radiation, making it totally invisible to our telescopes. So, how do we even know it exists? The evidence is overwhelming, starting with galactic rotation curves. Back in the 1930s, astronomers like Fritz Zwicky noticed something odd. Stars at the edges of galaxies orbit way faster than they should based on the visible mass alone. If only the stars and gas we see were pulling them, those outer stars should fly off into space. But they don't. They're held in place by extra gravity from unseen mass, forming what's called a dark matter halo around galaxies. Take our Milky Way. Its outer stars zip around at speeds suggesting 5 times more mass than what's visible. Another smoking gun is gravitational lensing. Einstein's general relativity tells us massive objects bend light. We see this when distant quasars or galaxies appear distorted, like through a cosmic lens. In cases like the Bullet Cluster, 2 colliding galaxy clusters, the hot gas, visible in X-rays, separates from the gravitational lensing effects, which align with invisible mass. This shows dark matter isn't just modified gravity, it's real stuff that can be pulled apart from ordinary matter during collisions. Then there's the cosmic microwave background, or CMB, the afterglow of the Big Bang. This radiation blanket across the sky has tiny temperature ripples that match predictions only if dark matter was clumping matter in the early universe. Without it, the universe would be too smooth. No galaxies, no stars, no us. Galaxy formation itself relies on dark matter's gravity to pull ordinary matter together quickly after the Big Bang. Simulations without dark matter just don't match what we observe. But what is dark matter made of? That's the billion-dollar question. Scientists have several leading hypotheses. The most popular? Weakly interacting massive particles, or WIMPs. These are hypothetical particles, maybe 10 to 100 times heavier than a proton, that interact weakly with normal matter, mostly through gravity and the weak nuclear force. They're cold dark matter, moving slowly, which fits how structures formed in the universe. To find WIMPs, we build massive detectors deep underground to shield from cosmic rays. Experiments like Lux Zeppelin and Xenon NT use liquid xenon, waiting for a rare bump when a WIMP hits an atom. So far, nothing definitive, but these null results are narrowing down possibilities. Another contender, axions. These superlight particles were proposed to solve a puzzle in quantum chromodynamics and could make up dark matter if they're fuzzy or ultra-cold. The Axion Dark Matter Experiment, or ADMX, uses strong magnets to try converting axions into detectable microwaves. Again, no luck yet, but the search continues. Sterile neutrinos, ghostly particles that only feel gravity, are another idea, potentially explaining some neutrino anomalies. Or what about primordial black holes, tiny ones formed right after the Big Bang? Gravitational waves from LIGO might hint at them, but it's inconclusive. And then there's the outlier, modified gravity theories like MOND, which tweak Newton's laws instead of adding new particles. It explains some galaxy rotations but falls short on cosmic scales like the CMB. Why hasn't science cracked this yet? Detection is tough. Direct searches in labs look for those faint interactions, but if WIMPs are rarer or weaker than thought, we might miss them. Indirect detection scans the sky for annihilation signals, gamma rays or neutrinos, from dark matter particles smashing together in dense spots like galaxy centers. The Fermi telescope sees a gamma-ray excess in the Milky Way's core, but it could be pulsars, not dark matter. At particle accelerators like the Large Hadron Collider, we smash protons hoping to create dark matter particles. No dice so far, but upgrades might change that. The parameter space is huge. Particles could be super light or heavy, interact in weird ways, or even be a mix. Plus, if dark matter only chats via gravity, it might be undetectable with current tech. The implications are mind-blowing. Dark matter dictates the universe's architecture, from galaxy clusters to the web-like structure of cosmic voids. In particle physics, unveiling it could bridge gaps in the standard model, maybe explaining why there's more matter than antimatter, or even quantum gravity. Astrophysically, it stabilizes galaxies and influences black hole dynamics. Current efforts are ramping up. Next-gen detectors like Darman will be even more sensitive. Observatories like the Vera Rubin Observatory will map dark matter halos in unprecedented detail. Simulations like Illustrious TNG test ideas like self-interacting dark matter, where particles bounce off each other, solving small-scale puzzles. Dark matter remains a ghostly enigma, shaping the cosmos while hiding in plain sight, or rather, out of sight. If we detect it, physics changes forever. If not, we might rewrite gravity itself. What do you think it is? Drop your theories in the comments. Thanks for watching. Subscribe for more cosmic mysteries.